What's up, guys? It's Misha. Do you know this circuit? That's right, this is an inverting amplifier. Just two resistors and one op-amp. But have you ever been scared of analyzing such circuits with op-amp? I understand why. When you look inside this tiny little guy, you will find such a crazy circuit that might stop you from the further analysis. But I have good news. The first one, op-amp can be represented as a voltage-controlled voltage source. So instead of bunch of resistors and transistors, you have just two extra resistors and one dependent source. The analysis becomes easy. Let's look at the example. Say we have an inverting amplifier with input resistance 1 kilo ohm and feedback resistance is 10 kilo ohm. And you want to find the voltage gain of the circuit. When we use voltage-controlled voltage source representation of op-amp, we have the following circuit. In this circuit, Ri is input resistance of op-amp, which is usually very huge, say 10 mega ohms. The output resistance Ro, which is very small, say 10 ohms, and the open loop voltage gain A, which is also huge, say 10 to the power of 6. To solve for the voltage gain, we just do nodal analysis. Let's label this node A and write KCL equation for this node. So simplifying this equation, we have the following. Okay, and we do the same for output node. From the circuit, we can see that VD equals negative VA. So we substitute it into the second equation, and we simplify it to solve for VA. Now we substitute the equation for VA into the first equation, and we get the following. So rearrange it to get the voltage gain. We have V out over V in. So we get minus 9.999889881, which is very close to minus 10. We did it! How was it? Yes, took some time and attention to keep all the terms till the end. But now, there is a second good news. We can simplify the analysis even further using the ideal op-amp. We sacrifice some accuracy, but the analysis becomes much simpler. So, when we use the ideal op-amp, we make the following assumptions. Input currents are 0, and voltage at the inverting and non-inverted terminals are the same. Let's have a look at the same circuit, but now with an ideal op-amp. We will follow the same approach. We do nodal analysis. Let's label node A and the input current of the amp I minus. And let's write KCL equation for node A. And at this step, we need to apply the assumption of the ideal op-amp. We know that I minus equals 0, and the voltage at the non-inverting and inverting inputs are the same. So because the non-inverting input is grounded, the voltage VA equals 0. Let's rewrite KCL equation we have using the assumption of the ideal op-amp. And from this equation, we can easily see that the voltage gain is minus RF over Rin. Or if we substitute the value we have, we will get minus 10. Now let's compare with non-ideal case. We have the following circuit, and if we derive the voltage gain V out over V in for this circuit, we will get the following equation. And as you remember, we found that in our case it is minus 9.999889881. Analyzing the equation of the voltage gain with non-ideal op-amp, we can see that this term is very close to 1 and can be neglected in most of the analysis. We did it again. How was it? Now it took much less time and effort to do this, and the difference in the results is negligible. So, whatever circuit you have, analyze it with ideal op-amp and it will be accurately enough. I'm not sure if in aerospace it's a good practice to use ideal op-amp. Maybe you need more accurate result. If you know, tell me about it in the comments below. Meanwhile, practice in circuit analysis with op-amps. I'll give you one circuit, do analysis with non-ideal and ideal op-amp, and let me know the difference in the answers. If you like this video, hit the like button, share it with your friends, and subscribe to my channel. It was Misha. Thanks for being in the class today. Bye.